Here we go, let's get started. Okay, stop talking please. Let's get started. Here we go, let's get started. Stop talking please. Here we go. Are you ready to start? Stop talking please. Stop talking please. Thank you. Okay, let's talk about some announcements. So I put your scores out of 100 so that for a while there you had your score out of 28, but then the first 8 were worth less than the rest. So we got that adjusted score, the weighted score. And so then to get your score on this test, you're going to take now your score that's now posted, something like out of 100, and you're just going to add 1. Okay? The average was 71 and the median was 79 or something like this. So bravo! You guys did awesome. There were like 8 people that aced the test and something like 35 A's. Okay? And a whole host more B's. So lots of you are moving up. Lots of you are moving up, and that's awesome. Getting the hang of this course. So keep up your hard work. Again, so you're just going to go to that E2 score and just add 1. Add 1. Okay, so now some of you are curious about calculating your grade in the course. So I'm going to quickly do this. So the first thing you want to do is, don't do it now, but find your, so I'll just kind of write this out. And I'll put this on an announcement on Blackboard. So your quiz average, okay? First do your quiz average. That'll be out of 20. All right? And then you're going to multiply that by 5, so you get like an average out of 100. And so we'll call that number Q. So Q is your quiz average out of 100. So you take your quiz average, which is out of 20, multiply by that average by 5, and you get this number Q. So then what you're going to do is you're going to average together Q and your first 2 exam scores. So call E1 your adjusted exam 1 score. E2 is your adjusted exam 2 score after you added a point. And then Q, and then you're going to take the average of those. Does it make sense? So get that Q, get your quiz average out of 100, and then just average your exam 1 score, your exam 2 score, and your quiz average out of 100. And that will give you an average out of 100, and this is a baseline for your grade in the course right now. Okay? If your homework is really high across the board, then your grade in the class is higher than that baseline grade. If your homework is kind of average in the middle, you're missing some, you're getting maybe some C's, D's, B's, then your grade in the course is this baseline. If you're not turning in a lot of homework, you're getting really low grades on homework, then your course grade will be lower than this baseline. Does it make sense? So this will get you within 3% of what your grade is in the class by doing this, okay? It'll give you a good idea of where you're at. Any questions on that? Okay, so that is on the video, and I'll put it on Blackboard. So we talked about exam 2, we talked about grades. If you like this, okay. So I also on Blackboard on announcements, I'm going to be posting a new registration code for GC. Okay, so some of you are finding that your GC is starting to not work anymore, and that's because that initial license was just temporary. So I'm going to put a new registration code on Blackboard announcements. And so here's the thing, it's only 1 machine per student. You can only use that 1 machine per student. If lots of people abuse that, then we won't get the privilege of having this for free, okay? So that's kind of the trade-off. So we gotta be honest about that. Just 1 machine per student in this class. You can't be sharing it with students in other classes, and you can't put it on more than 1 machine. As long as we stick to that, then we're good to keep this as a free software for you to use, okay? Other questions? We'll go over most commonly missed items on the exam on Friday, okay? And if you want to see in particular exactly what you missed, we encourage you to come in and look your exams over. We'll get you your feedback sheet. We'll get you the test you wrote on. So the best way to do that is to come to my office hours. I have them all. But if you absolutely can't come to my office hours, then we'll arrange for you to do that in other student TA's office hours. Okay? But encourage you to come in, look over your exam, find out what you missed, where you went wrong. And we'll take as much time as you want to go over those. Okay. Any questions or maybe other announcements, TAs, that you can think of. Okay, cool. So let's do this. Get this handout. We split up here. You can start working on the first page as soon as you get it. Everyone down here, come on. Yes. Okay. You start working on the front page. Thank you. Okay, so now what we used to call delta x, we're now going to call h, a little more compact, a little more efficient notation. So h has the same meaning as delta x did before, okay, h. Okay, so I warned you Wednesday, lots of you are doing this. On Monday, you resoundingly told me that this is not right as a class, but now lots of people are doing it. This is accumulation. This is like, think of amount or amount accumulated. So what's happening, if you do this, then what are you saying about the accumulation? It's staying the same. It's staying at the same value. So then what's the rate of change for that? Zero. Zero rate of change. So then what do you get for your rate of change graph if you do this? Zero. It's all zero. Do you see that? This is not a rate graph. This is how much you have accumulating by every moment. So if you do horizontal lines, you're saying that your amount is staying the same and your rate of change is zero. And so then if you build a rate of change graph off of those steps, you're just going to get zero rate of change. So we have to know what an approximate accumulation function looks like when we start with an exact accumulation function. We're trying to mimic this increase and decrease with constant rates. Not zero rate. Not zero rate. You see? Okay, so we were pretty good as a class Monday, but then we forgot. The homework was just to help, not hurt. So if you drew horizontal lines, erase and start over. This is not the approximate accumulation function that we have. Okay, so I'm glad we did this activity. Lots of you are having trouble making sense of this, okay? So what you should have for your approximate rate function is constant rates, which are linear segments that are trying to be like the actual accumulation function. That's over here on the right. That's your approximate accumulation. Okay? So now if we're going to draw a rate of change, well, the whole point was we've made an approximate accumulation to be based on constant rates. Okay? And we know what a constant rate of change looks like. It's a horizontal line on a rate of change graph. So then we have to look at this first one and say, is this a high or low, positive or negative rate? Is that a high or low, negative or positive rate? It's a high, positive, constant rate of change. So how will that graph as a rate of change? Well, constant rate of change will be horizontal and here a high positive value. The next one, positive or negative rate? Positive. Less or more positive than the one before? Less positive. Right? For a change in x, you don't get as much change in y on this one. So you get a lower constant rate, but still positive. The third one is also a little bit lower positive. And then over here, rate of change here. Positive or negative? Negative. Our accumulation is decreasing. We're de-accumulating, right? We're de-accumulating. And so what does that mean for rate of change? Changes in y are negative for changes in x. But it's not, it's kind of at a low rate, a low negative rate. So that's going to be down here. And then the next one's a more negative rate of change, so more negative. So this is what the approximate rate of change looks like. It's going to be our step function, right? It's going to be our constant rates as steps. And then to get some kind of so the exact rate of change function, we imagine that h getting smaller. Get that h getting smaller, we'd have lots of more smaller steps. And eventually, we're going to get something like this. Okay? Imagine a million little steps, right? A million little steps that have very low change in x. Questions on this? Questions on this? Okay, so we'll leave that second one up to you to keep thinking about. Questions on that before I go on? Questions on that procedure? Does it make sense? Okay, so let's flip over the second page. So you can confirm, do number 2 on your own, or if you didn't finish it, make sure you confirm you can do that correctly. So let's look at page 2. So we're going to start with changes of 0.4. Changes of 0.4. So imagine x is increasing through intervals of h of 0.4. So that's what this would look like. Okay? So sketch for 0.4, sketch f's approximate accumulation function, and we'll call that approximate accumulation g on the right. So along with exact accumulation, you're going to sketch approximate accumulation. So after the one we just did, we should all have that, no problem, right? Here's what it should look like. Now I'm showing it being generated, right? Being generated, because that's our image of graphs. When we see a graph, we know that it came about point by point at some period of time. There was some point in time where that graph came about point by point as two quantities changed, right? So that's when you have a graph. That's your image of the graph, like that. Okay, so now, let's pause it here. So we want to write this function, right? Can we write this function one more time? So that means we need, now this is any interval. So I'm going to look at this second interval here, but it can be any interval. So to do that, then we need, what is that ordered pair right there? So actually, let me move back into this interval. Okay, so here we're in this is an arbitrary interval. This is any interval. So I'm showing the second, but it could be any interval. How can we say what the coordinates of that, if this is the function f, what are the coordinates of that point right there? Let's see. Jacob Harvey. Harvey, yeah. Can you tell me what the coordinates of that point would be? If this is any interval now, so we're halfway through any interval, do you know what the coordinates of that point would be? Jacob?
So would it be 0.4 and 4?
Yeah, but this is any interval, not the second interval. Any interval. So the numbers aren't going to help us because this could be the fifth interval, the eighth interval. Okay, this Jacob.
Would it be left x?
Left x? F of left x. That's the point of any interval, right? Any interval. Okay, now we want to write the coordinates of this point, and basically the y-coordinate of this point is representing this approximate accumulation function, the y-coordinate of that point right there. Okay, so this is x, g of x. And we're going to build g of x, right? So that point is the current value of x, and this function that we're building, the approximate accumulation function, g of x. So how are we going to, what's going to be the general structure of g of x, the most general structure of g of x? Right, we've got this, what? F of left of x is what? A starting y value. And what are we going to do? Aiden. Right. Piecewise linear functions. We can do y initial plus the change in y. What's our y initial? F of left of x is our y initial. How are we going to get the change in y? Somebody new. How are we going to get the change in y? We've done this many times before. Huh?
MDX.
MDX. Okay, so we need m, and what's dx going to be? It's not h because we're partly through the interval, right? So this, our dx then is this. I'm not going to have to do with h. X.
X minus left.
Minus left x. Okay, what is m? So how do we get this rate of change? Who remembers? How do we get that rate of change? Yes, sir? What's that?
The change by top of g of x minus f of x.
No, it's not. So we got to think about this extending to here, and we're gonna use these 2 points to get the rate, the starting and ending point of our h interval. So we can't use that point because it's the one we're trying to find. So we're going to use these 2 points. So what's the coordinates of that point? Yes, sir?
F of left of x plus h.
Not f. X coordinate first.
Oh, you want the point. So that will be x left x plus h.
Left of x plus h. This is now the end of the interval. And f of that. And then so now so we want the constant rate of change in this interval. We've got the starting point, we've got the finished point. What do we do? Somebody new. What do we do to get the constant rate in this interval? Yes, ma'am. F of left of x, so y final. Minus y initial gives us the change in y, right? dy over. So we could write a bunch of stuff out, or we could just say the change in x is just h, right? So if we could write all that stuff out, but in the end, it's just going to be h. It's just going to be h. Okay, so then that's our g function. So what g of x was the y coordinate of any point on that approximate accumulation function, and it's this right here, and then that m is this up here. So this thing right here goes there, right? Okay, so what will the approximate rate function look like? So that's that function that I'm showing in purple or pink, something between. This is the function g. This is the function g. In any given interval, it's the starting value of y plus the change in x, which is that constant rate for that interval, times x minus left of x, which is dx. So y initial plus change in y, or plus m dx. Okay, so what will the approximate rate function look like? Sketch that. Sketch the is that the next thing to do here? Yep, sketch r, the approximate rate function. And then I want you to write out what that function is. Right? What is r of x? So sketch the approximate rate function. Now it's saying to use values. So just to make it really easy, call this y value 4, okay? Make it really easy. We'll call this one 4. Call this y value, call it 5. And then call the last y value 5.5, okay? We'll make it really easy. So first y value is 4. Second y value 5. Third y value 5.5. Those are not good estimates, but it'll make the math easy, okay? So we're going to estimating those constant rates. Maybe better would have been 4, 5.5, and 6. Let's do that. Y value 4, this point, y value 5.5, y value 6. So what's the first rate? What's the first constant rate? Using a y estimate of 4 for that point. 4 divided by change in y4, change in x, 0.4 gives you 10. And so what will this graph look like if our first approximate rate, we're saying it's about 10 for 0.4, yeah.
Be a horizontal line from 0.4 to 10.
Right. It's going to look like that. What's that? At 0.4? Oh, did I not make it far enough? Okay, well, you got the idea. So let's show it here. Are you finding the other two? Why isn't it showing up? Oh, 3 is just the equation, okay. Okay, so yeah, so something like 10. So what about the next? What did you get for the next? Change in y should have been 1.5. Change in x, 0.4 gives you what rate? Nice and loud, anybody? 3.75? 3.75. So let's watch it happen here. Ready? Something close to 3.75. Okay, next one. So change in x was 0.5. Change in y 0.4 gives a rate of change of 1.2. Watch it. There it is. From 0.8 to 1.2. Approximate rate of change, right? Constant rates that are positive and getting less positive. Okay, what is the rule for R? What is the rule for R? So I want to write a function that gives me, write a rule that gives me that whole function there. Who's on top of this? Yeah.
The f of left of x plus h minus f of left of x over h.
So are you looking at this right here? And why are you saying that that's it? Why is that it?
Because that is our rate.
Yeah.
Why would we do this?
Good, you got it. Right, so we already did it. We already did it. It's what we called m before, right? It's this thing right here. This is the function that gives us the constant rate in every interval. Right there, this thing, and so I think it'll show up here. Yeah, there it is. It's the f of left of x plus h minus left of left of x over minus f of left of x all over h. Okay, so see how much faster this reverse process is going, right? The forward process took us a month at least. Here we are, and we're just about to get an exact rate function. We're about to get an exact rate function. How are we going to get the exact rate function now? Or what does that look like to move towards a better somebody new? Yes, sir?
Just make h really, really tiny.
Okay, so if we make h smaller, every time we make h smaller, we're going to get a better approximate accumulation function. We're going to get a better approximate rate function. So here's a smaller h. Watch. So notice there's less daylight between our approximate accumulation, those lines, those segments, and the exact accumulation. Again, here's a smaller h again. And now we can barely see the difference, right? We can barely see the difference between approximate and actual accumulation. Here's a really small h. And so you can see the actual rate function starting to form, right? The continuous rate function. So what's the smallest h I got here? There's h of 0.005. But those are still, if I zoom in over there, I can't grab on there. Look what happens if I zoom in. Double vision. There's still constant rates, okay? There's still little constant rates. Clicking the wrong one. Okay. But with a really small h, we get something very, very close to the exact rate function for this accumulation what? Positive, getting less positive, right? Rate of change is positive, getting less positive. There it is. Rate of change positive, starting high, getting less positive, coming down. Okay. Questions on this process? Okay, so our goal is to get this as a closed form. So remember what a closed form is. Closed form is computable, rapid fire results, right? Rapid fire values of the dependent variable. This doesn't lend itself nice to closed form. Okay? So not helpful for achieving closed form. This is good. This has been good in that we've seen exactly the reverse process of what we did before. But we kind of come to something where we need to make an adjustment. We need to make an adjustment to our approach over here, to the accumulation function, so that we can get something that's more helpful in achieving closed form for an exact rate function. That's what we want. Closed form. Okay? So let's put our h back to 0.4, and we're going to do an enhanced version of this, or a different version of this. And this is what your quiz will be. Friday's quiz will be what we're about to do now, okay? Or have to do with. Okay, so here's how we're going to make a transition. So this is what we've been doing, right? This is what we've been doing. What do we have? We have these fixed intervals of h through which x changes, and in each interval we get a constant rate, right? That's what we've been doing. So now what if we look at h this way instead? So notice at the beginning, so we got the same thing at the beginning of every interval, but then what happens in the intervals? When x is in the intervals, instead of holding on to the rate that we have for that whole interval, based on the start and end points, what if we let that interval of h slide along with x? So question 1 there, or question 4a, will the resulting rates of change be constant rates that change abruptly, or something else? So now if I'm going to calculate rate of change based on the blue h that always stays with its left side at the current value of x. What will the approximate rate function look like? Will it change abruptly? Will it be exact? So let's take off the previous version and let's look at this newer version. So what are we going to do? We're going to take, for any given x, we're going to look at this interval that starts at x. And we're going to calculate a rate of change. How are we going to calculate the rate of change? Same way we did before. Okay? We're going to consider what? We're going to consider a constant rate of change, but it's just that no matter what value of x we start at, that's going to be the left side of our interval. So are we going to get approximate or exact rate of change? Is it? So now, here's x at something like 0.35, something close to 0.35. So at x equals 0.35, am I going to get an approximate rate of change or an exact rate of change? So if I zoom in on this point right here, until we get what? Local linearity. Do you see that our exact rate of change is represented by the curve, which is in a moment now? It looks like a line. And if we calculate it based on the h interval, are we going to get a lower or higher rate of change? Lower. We're going to get a slightly lower rate of change, right? Based on the h interval, that's the blue line. We're going to get a slightly lower rate of change. Okay, so let's write that rate function. So what do we need? We need, and this is, you guys can do this, and you can do it fast. What is the coordinates of that point? This is easier now. This is in fact easier. Okay, everyone do it. What's the coordinates of that point? Write the rate of change of that approximate rate of change of that blue line. So write the coordinates of those 2 points, which is now actually easier. And then write the rate of change, the constant rate of change represented by that blue line, which will be our approximate rate of change at the current value of x. First point is x and f of x. The second point is x plus h. This is nicer, right? I know we're a little bit over, okay? I know. All right, so what is the rate of change of that blue line? Everyone write it down. Everyone write it down. So here is as x increases, here's what we get when we, for all those values of the rate of change of that blue secant line. Secant meaning cuts through, that blue secant line. So is it approximate or exact rate of change, that blue graph? Still approximate. It's still approximate. And what is our, this is the revised version of this rate using the sliding interval. Using the sliding interval, should have gotten change in y, f of x plus h minus f of x, over h. Is this new approximate rate function. It's still the same as the old one when x hits the beginning of every interval. But now it's different inside the interval. Okay, written quiz Friday. Written quiz Friday.